Good morning, everyone. Welcome to SSO Wars, the Token Menace in South Pacific with Alexander Mirosh and Alvaro Munoz. Before we begin, we have a few brief announcements. Please stop by the business hall located in the Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2 during the day and for the welcome reception at 5:30 tonight. The Black Hat Arsenal is in the business hall on level 2. Please join us for the Pony Awards in Lagoon GHI at 6:30 today. Lunch will be available in Bayside AB from 12:05 to 1:30. And don't forget the merchandise store on level 2 and session recordings from Source of Knowledge. They have a desk on every level. Please ensure that your phones have been placed on vibrate to avoid interrupting the presentation. And now, please welcome Alexander and Alvaro.
So thank you very much. As he said, my name is Alvaro Munoz. He's Alexander Mirosh. We are both security researchers with Microfocus Fortify team. We have a packed agenda for today because we actually submitted this talk as a 15 minutes briefing, but it got accepted as a 25 one. So we had to discard a lot of stuff, but we put that into a white paper that is going to be published today and hosted in the Black Hat server. So we will start with a brief introduction to what authentication tokens are and how are they connected to delegated authentication. And then we will be presenting two vulnerabilities that we found in .NET framework. The first one is an injection vulnerability leading to arbitrary constructor invocation, and we will see what's the impact of an arbitrary constructor. And the second one will be XML signature bypass that we found and how we applied that to bypass the SAML signature bypass. That's what we call dupe key confusion. And we will be presenting what Microsoft frameworks and products are affected by this vulnerability. So delegated authentication is nothing else that when the user accesses a protected resource, the service provider who is serving this resource is not handling authentication itself, right? So it's basically delegating the authentication to someone else. In this case, we call it identity provider. So the user will go to the identity provider, will present the credentials, and upon validation or verification of the credentials, the identity provider will issue an authentication token for this user. So there are multiple formats of authentication tokens, right? We have SAML, we have JSON Web Tokens, we have Simple Web Tokens, we have many of them. But all of them share some attributes and some properties, and the most important one is the signature, right? Because if we don't sign the authentication token, anyone can change the token. The user or any attacker in the middle can change any of the properties or attributes of the authentication token and then just become anyone in the target system, in this case, in the service provider. So we will be focusing our research in step number 6. That is when the service provider receives the authentication tokens. And the reason for that is because we think that there are two very interesting attack vectors here. The first one is when the service provider needs to parse and process the authentication tokens, some of these attributes need to be parsed before the signature is verified. So if we can find one attribute that can lead to an injection vulnerability, this will be before the verification of the signature. The second vector will be what if we can go one step further and actually try to bypass the whole signature verification altogether. So if we can do that, we can basically craft any authentication tokens for any arbitrary user, present that to the service provider, and get that accepted as a valid token. So we will start with the token parsing vulnerability that we found in .NET.
This case can be a good illustration for token parsing vulnerabilities. For signature verification, server needs a couple object that represents algorithms, crypto algorithms, and usually crypto config create for name method is used for their creation. But we noticed that it does not restrict type names, so we are able to call any no argument public constructor. But you can ask, can it be dangerous if we cannot control any data? But actually we can control some data. First of all, type name itself is under our control. Also, we can control some part of current HTTP context, and some constructor can use it. Other question, how we can reach this method. For example, a system identity model tokens GWT library passes ALG field from GWT header to it. Also, algorithm attribute of signature method element from SAML token goes without any restriction to it as well. So we took two Microsoft servers, SharePoint and Exchange server, and tried to exploit this problem there. And here is a list of our results. SharePoint returned us different results for successful creation of object and not. Using this, we were able to get information about installed product and their versions. Also, we could raise unhandled exceptions that can lead to a denial of services. For Exchange server, as an authenticated user, we were able to invoke any arbitrary public no-argument constructor from any DLL or exe file from arbitrary folder, local folder. Unfortunately, we do not have time to cover it today, but you can find all details in our white paper. Let's switch to our Holy Grail and let's look how the entire signature verification can be bypassed. Security assertion markup language, or just SAML tokens, has XML-based format and uses XML signature for integrity protection. We can see simplified SAML token on the screen. Along with the authentication information itself, it contains signature element that should protect it from tampering. This element contains three main parts: signature itself in signature value, SIGNIT info has information how this signature should be verified, and the most interesting element for our attack is key info, represents key that should be used for signature verification. Let's review how .NET implements signature verification for such tokens. First of all, we need to obtain key. Using key info element, we can extract this key from it or use key reference and fetch key from some storage. On the second step, we will use this key for signature value verification. But please note, positive results after this step only means that this specific token was signed by this specific key and was not changed. In addition to this, we need to be sure that it was done by proper signing party. So we are taking key info element again and try to identify who has signed this token. And of course, the last step, we will check it is expected signing party or not. Here we highlighted the key steps for our attack. So we are taking key info element twice on different steps. Also, we need different types of results on this step: security key and security token. So we will call two different methods: resolve security key and resolve security token. On this diagram, we can see the general idea of attack. We need to craft key info element in such a way that we will get different results from resolve security key and resolve security token. One will be used for signature verification, another for authentication of signing party. In this case, we will be able to use own key for signature calculation, but servers still identifying us as expected signing party, and we can bypass the whole signature verification and can create some token with any information. This problem affects all places where in .NET where XML signature is used, including a product that works with SAML tokens. Let's review the key frameworks of .NET that use SAML token now.
So we will start with Windows Communication Foundation, which is or WCF, which is a Microsoft framework to build web services, right? They follow the service-oriented architecture, but what is interesting for us is that WCF web services will accept SAML tokens for authenticating the client, right? So the client can go and present valid credentials in the form of maybe user and password, but also a valid SAML token issued by an identity provider. So the class that is responsible for handling SAML tokens in WCF is this SAML assertion type. And this piece of code as you can see that there are two different method invocations. One is resolve security key, and the other one is resolve security token, but both of them take the same parameter, right? That key identifier parameter contains the whole key info section. That is all the different keys in the key info section. The first one will return the verification key. That is the key that will be used to verify the signature. And the second one will return the signing token or the security token that is used to represent somehow the signing party or the identity provider. So if we focus on the first one, when resolving the key, what we will be doing is what we call depth first. We will be first iterating through all the different keys in the key info section. And for each of them, we will be invoking this try resolve security key that will basically try a number of resolvers for those keys, right? So first we iterate through all the keys, then we iterate through all the resolvers. Now for the token resolution, the approach is slightly different. Instead of iterating first through all the keys, it will iterate first through all the resolvers. It will try all the resolvers, and then for each resolver, it will try all the keys. So what we can do is actually abuse that, because even if this difference is very small, we will end up visiting all the combinations of keys and resolvers, but in different order, right? So we can abuse that, and this is what we will be doing for attacking, for example, WCF web services like Exchange. So first of all, we can modify an existing SAML token or create one from scratch. Then we will create a pair of RSA keys with public-private keys, and then we will use the private one to sign the token. Then we will send both the public key for this RSA pair and also the certificate or the key identifier from the identity provider. So we will have something like this in the key info section, right? First, the attacker RSA key, and then the expected key identifier. So the resolve security key will iterate through all the keys first, then it will take the attacker one, and then it will try all the resolvers. The third one will succeed, and then it will return the public key from this RSA pair. Since we signed our token with the private one, the signature verification will be successful, and we will bypass this authentication. Now, when resolving the security token, because we are going to iterate first through the resolvers, we will start with the first one and then try all the keys for this particular resolver. So the first resolver doesn't know how to resolve an RSA key, so it will fail and we'll move to the next one. The next one is the identity provider certificate. So it will succeed, we'll return that, and then the first one will be used for signature verification, the second one will be used to authenticate the signing party, and therefore we will be able to bypass the process. So this is how it looks in the XML SAML assertion. The first element in yellow is the injected key. In this case, we are using an RSA key. We can also use elliptic curve keys or symmetric keys. And the second one in green is the expected identity provider certificate that the server trusts and expects. So let's see that in action. We will be actually taking over any account in Exchange by abusing the Exchange web services. So instead of using a real client such as Outlook or Link, we decided to actually create our own client in order to make the demo more visual and more simple to follow. So we will be intercepting, so we have Verb here, that is an interception proxy. What we are going to do is we are going to intercept the request from the client. So this is our simple client. It's basically going to request the mail tips or the mail item, for example, could be another valid request for user one, right? And it's going to authenticate as user one and ask for their mail items. So we will send that and we will intercept the request. Now we will be sending the request to repeater. That is an easy way to modify the request. And if we switch to the XML view, we will see the SAML assertion. And for example, the subject is the user one, but we will be replacing all instances of user one with administrator. Now the attack is to become administrator and read administrator mail tips. Now, because we are not changing the signature, if anyone do this kind of attack, it's going to fail because the signature is no longer matching the content of the assertion and the body of the request. So if we send that, we get an error that is the expected result. We tampered with the request with assertion, and that's not valid. Now, if we use one Verb plugin that we developed, that will allow us to resign the token. So as you can see here, in the key info section, we only have the original identity provider certificate. But now if we click on resign with RSA key, we will be basically resigning it with our own private RSA key and then appending the public one to the key info section. So we have the original one, the identity provider one, but before that we have the RSA key that we use to resign. And this one will be used for verifying the signature. So with that, we send the request, we get a 200 successful response, and we are able to get the mail tips from the administrator. This is successful, no error response, and the attack was successful. Okay, so bear in mind that this was we were attacking an on-premise service, on-premise Exchange server, but this was valid for the cloud version, right, for Office 365. So we were able to actually access any mail from anybody using Office 365. Now we will be reviewing Windows Identity Foundation. For those of you that are not familiar with WIF, it's basically a framework for developers to integrate with identity providers. So it will take care of all the process of handling the authentication tokens, verifying the tokens, extracting the claims, and then providing the claims to the application to take claim or identity-based decisions. So WIF uses a different set of resolvers. But what's interesting in WIF is that for key resolution, it will only try to resolve the first element in the key info section. But for token resolution, it will try to iterate through all the different elements in the key info section. So we can abuse that by providing a key that is supported by the key resolver, but not for the token resolver. So WIF uses this token, issuer token resolver, which is secure because it handles both tokens and keys in a similar way, consistent way, and then we can't abuse this resolver. However, if it fails to resolve the key or the token, it will move to the next resolver, which is this 509 certificate store token resolver. Now, this one is interesting because when resolving security keys, it supports encrypted symmetric keys, but when resolving security tokens, it does not support encrypted symmetric keys. So in order for the server or the application to decrypt our encrypted symmetric key, it needs to use a private key that is stored in a specific certificate storage in the server. Therefore, the attacker needs to get access to the public key from that certificate in order to encrypt the symmetric key. That's a strong limitation, but maybe in some cases, for example, the certificates are reused for SSL traffic, and then attacker can get the public key from the certificate for the SSL traffic. So if the attacker gets access to this certificate, the attack flow is as follows. The attacker can change or modify existing claims. Then it will use a symmetric key to resign the token, and then it will encrypt that symmetric key using the certificate from the server. Now it will include both the encrypted key, but also the original identity provider, and the process is very similar. It will lead to this duplication of keys, where the first one that is attacker controlled will be used for signature verification, and the second one that is the identity provider trusted certificate will be used for authentication of the signing party. So that was the default configuration for WIF. Now, if you are building an application using WIF, you can customize. You can change, for example, the location of that certificate storage, but you can also, for example, customize the resolvers. And that's exactly what SharePoint is doing. So SharePoint uses WIF to handle the authentication tokens, but it uses a custom resolver. And SharePoint resolver, when resolving security keys, supports things like asymmetric key, RSA keys, elliptic curve keys, but when resolving security token, it does not. And obviously, we can abuse that. Therefore, we can attack SharePoint, which is using WIF without the limitations of WIF. And with that, we were able to attack and get access to any SharePoint, again, on-premise and also Office 365. So conclusions and takeaways. First of all, we're not saying that SAML or WS Federation are insecure protocols. These are, in this case, a design flaw in the implementation, specifically in the .NET implementation of the XML signature verifiers. Actually, the root problem here was that we had these two different methods which were taking user control data, and they were inconsistent in the sense that we were able to force them to return different objects. So that's very interesting from a security standpoint. If you are reviewing code, you want to look into these kind of methods. But for example, if you are writing your own applications that integrate with WIF, you want to make sure that if you are customizing the resolvers, they are consistent and they are not returning different elements. Also, we focus our research in .NET. One of the reasons is that .NET was secure for all the previous attacks and for SAML tokens. But we did not spend a lot of time, or actually we didn't really look into other languages and frameworks. So we don't expect the same design flow to exist in other languages because it's somehow .NET specific, but similar things, similar flows can appear in other languages and frameworks. Even in .NET, remember this is a bug that is affecting the verification of XML signature, not only SAML assertions. So even in .NET, XML signature is used for many other purposes. And we found a couple of cases where it was also insecure. We reported that to Microsoft and they patched that, but there may be others. So the main takeaway is patch as soon as possible, and follow Microsoft recommendations for this CVE, because, for example, for SharePoint, you need to update the SharePoint version, but also need to update some of the .NET Framework libraries in the system. So it's not straightforward. Also, we are releasing the Bear plugin that we developed for our internal testing. So basically, will allow you to intercept SAML tokens and resign them using either an asymmetric RSA key or the public key from a certificate in the case of WIF applications, if you can get access to that certificate. And with that, if you have any questions, we still have 4 minutes. Otherwise, we can go to the wrap room, or you can just send out your questions to our Twitter accounts, and we will be happy to answer them. Thank you.